Hello friends, welcome back to my channel. In today's tutorial, I will teach you how to make some cool population change maps for any country in the world. We'll be using the example of Romania, an Eastern European country that has seen a huge population decline since the fall of communism in 1990. More precisely, Romania has lost over 4 million people between 1990 and 2021. We will take 3 steps to glory. The first step will be to download, unzip, and then load global human settlement layer data into R. Our second step would be to calculate population change between 1990 and 2020 using this global human settlement layer data. And our third step will be to create some cool population change map of Romania. Welcome back to R, where we will first of all install and then load the packages that we need in this session. I'm going to define here a list of libraries that we want to install and then load. The first one is the umbrella package Tidyverse, which we will use for data wrangling and data visualization. Among these one, we will be using dplyr for data wrangling and ggplot2 for creating our map. The second one is the Terra package, which is going to help us deal with raster files, and we're going to be using some population raster files in this tutorial. The third one is GHSL, which we will use to fetch the national boundaries of Romania. Romania is the country that we want to analyze today. So these are the only 3 that we currently need. So let's go ahead and first of all install these libraries. Well, first of all, we need to check if they are already installed. So what we're going to do here is we're going to take this list of libs, and then we're going to go into the row names of already installed packages. And then this is going to actually give us more information about whether these packages are installed or not. If they're not installed, then we need to install them. How do we do that? Well, if any of the installed libraries equals false, then we open this curly brackets, means we need to do something. Well, in that case, we're going to install packages, but we're not going to install all the packages. We're going to install those among libs that are not in the installed libs. So that's the trick. Okay, so this will then install the packages that we don't have. And the final one is to load the packages. So loading is quite easy. We just simply need to apply a library function to our list, which is called libs. And library function in R is used for loading everything into R. In today's tutorial, we'll be mapping population change, and for that purpose, we'll be once more using global human settlement layer. Global human settlement layer is the raster product, which denotes the number of people per cell. And this is estimated at 5 years intervals, starting from, as you can see, 1975, going all the way to 2030. So these are the estimates, but these estimates are based on disaggregated data from census or administrative units, and then they are mapped to grid cells. So what this actually allows us is for every cell of a certain area, we will have some kind of a population count. So if you are interested more about this data set and how is it built and what is the methodology of it, what you can do is you can actually click on this GHSL data package 2023 report and read carefully through it. What is important for us in this tutorial, we'll be using the resolution, which is 30 arc seconds. And this is in the standard WGS84 coordinates reference system. But we can also go for even higher resolution. So we can go for, let's say, 3 arc seconds. The only thing is we'll be downloading here the entire data set. So we'll be downloading the entire one. And if we go for 3 arc seconds, it's going to be a pretty bulky one. It's going to be actually a few GBs of data. So I'm going to go for a smaller one and also poor resolution. But if you feel like you want to produce a map with a higher, you can definitely go for this 3 arc seconds in this case. So what is actually important now with that we are in this master dashboard is you need to click here on this GHS dash pop, and this is going to take you to this GHS population grid. So it was updated 2023, so this is a new version. Now we want to actually compute population change between 1990, so that was the first year or one of the last years actually before the fall of socialism in Central and Eastern Europe, and we're going to take some kind of a kind of greater horizon, let's say we're gonna look until 2020. So those are gonna be 30 years. And let's see within those 30 years how much the population has changed. So the first thing actually to do is then, since we're gonna work with 1990 and 2020, to copy the links or actually download. So if you want to download, you can download here. So there is a link which says download the global and then the name. So what you can simply do is we're going to be using 30 arc seconds. So I just come back to this one. You can simply click here and then put into your own working directory. But what we're going to do is I'm going to copy now this link for 2020, and then I'm going to go and navigate to 1990 and also copy this link. And once I copy these two links, I'm gonna go back into R, and then within R, we're gonna go and download programmatically these two raster files to our local drive and then load them into R and then work with that. If you decided to download the data programmatically in R, then I copied and pasted those two URLs for each of the years, 1990 and 2020. And they're quite long, as you can see. But what we will do next is we will define these as URLs. So I'm going to go ahead and say here, these are URLs. I'm going to put them into a brackets here. And I'm going to add this C, which means that it's a list. The second thing is I'm going to turn this into strings. And in R, to turn into strings, you need to use double quotation marks. So that's how you do it. So once we actually define this, we need to download using, of course, these URLs. So because this is a list of URLs, we also need to use a for loop. So I'm going to say here for URL in URLs, and then I'm again going to open this curly brackets and use download.file from base R. So here for URL, it's any individual URL that we want to use for downloading. Then the path is going to be the main working directory, and then the final one is the destination file. This one is going to be the base name of each of these URLs. Okay, and then once you run all this, this will initiate the download. If you have any problem with the download, before you even type this for loop and before you even execute it, maybe what you can do is increase the timeout, because I know some user had this problem in the past downloading files through R. So this is what you can do. You can change your global option. So you can set here timeout, and then this is in the number of seconds. So let's say the usual one is just 1 minute timeout, so 60 seconds. We can actually increase this, let's say, to 300 seconds, which is going to be 5 minutes. But you can go, and increase this even more if it's needed. So totally depends on your internet connection. I'm just giving here you the options. All right, so we run all this. We download those two files. And then the next thing is to unzip them, because they come in a zip format. So here, again, we need to apply, but this time we need to apply the unzip function from base R, and we will apply this to, again, the base name of all the URLs. Okay, and we can now load those two files into R, and we're going to load them as a list. So list of two raster files, one from 1990 and the other one for 2020. So first of all, we need to enlist these files to see what is out there. So what I'm going to do is use list.files from base R. Then for the pathway, again, I'm going to use the main working directory, because this is where I also downloaded those files. Then I need some kind of a pattern for recognition. So I'm just going to use here TIFF. And I'm going to add this $sign at the end, because once you unzip those files, there will be another one which is going to have this TIFF extension. So you're making sure you're using TIFF $sign that you only get the TIFF files here. And the final one is I want the full path to these files. Okay, so what we can do is simply run this. And once we run that, I want to show you how these file names look like. So we run this, file names, and as you can see, we really captured those two TIFF files. So one is for 1990, the other one is for 2020. All right, going back to our editor, the last step here is to load them as a list of two raster files. So I'm going to call this pop rasters. And with Terra, it's really easy. You just need to use Terra Rust. But because this is a list, we need to, of course, append to this. We need to put lapply, because we are applying to the list. And in our case, the list is called file names. Okay, it's as easy as this. All right, so then you can simply run this, of course. And once you run that, I want to inspect with you together this pop rasters. did we really get here the list? So yes, we did. So here's the first list. So the first member of the list is the population estimates for 1990, as you can see. And the second member of the list is the estimations for 2020 year. How do I know that? Because the names are actually the names of the raster files that we download. Here you can also see the minimum and maximum also values for the population count for each of these rasters. What you can also see, and it's really important for us, the dimensions of both rasters are the same, and also the resolution is the same, and also the extent. This will allow us to do further raster analysis where we actually calculate the change of population between those 2 years. Because these raster files are for the entire globe, we need to crop only the extent for Romania, and it needs to fit the Romanian borders. So we will go to rescue GHSL. So I'm going to go here and I'm going to make a function which is going to be called get country borders. And then this function is going to call GHSL. As simple as that. So within this one, I'm going to name this one country. And then I'm going to call GHSL. And then GHSL get countries is the actual function that will do this for us. Then we need to define the country. Here you can put ISO2 code. So for Romania, it's RO. And finally, you also can choose here if you want a resolution. So I'm going to go for resolution 1, which is the crispest, but you can also check this function and it offers different ones. The most coarse resolution is 60, which is 1 to 60 million. All right. And once we define this, we need to also return this country object, as with every programming language. And then we can call this function outside of this. And we can assign this to this country object. Okay, so we have the global rasters, we have the national boundaries of Romania in the SF format. Now we can use those boundaries to clip the global rasters to the extent of Romania. And this is how we're going to do that. I'm going to first of all, and remember we're still working with lists, so I'm going to create country pop rasters. And I'm going to use then, again, lapply because we're still working with functions. So I'm going to apply to this pop rasters. I'm going to apply a function. This function is going to do what we just said. It's going to clip. So it's going to clip those global raster files to the extent of Romania. So for that, we need to use terracrop. And then within terracrop, there are several things. Well, first of all is this element of the function. So that's X that we're going to pass to it. In our case, that's pop rasters. The second one is that country SF file. Now, the thing is, if you want to work with Terra, with this one, you need to coerce it to a Terra-friendly format or a Terra vector format. So that's why we're using this Terra vect and we're coercing this country object to it. Okay, so that's the first one. And then there are 2 more options that we should put here. Next one is that we want to snap everything that is inside of the Romanian polygons. And the last argument is to mask everything that is outside of it, which means get rid of everything that is outside the Romanian national boundaries. In other words, turn that into NA values. Okay, guys, we cropped those 2 rasters, and now we have the population rasters for Romania for both 2020 and 1990. Our next step will be to calculate the population difference between those 2 years for each of the pixels. So before we jump straight into that, I just wanted to share here that I will be again using the Lambert projection since I'm working with a European country. So if you're working and running this code for a non-European country, you can actually skip this part where I define this and then wherever I use this CRS_Lambert. All right, so calculating difference between 2 rasters in terms of their pixel values is very straightforward in Terra. Here's how we do it. I'm going to define, first of all, an object called popChange. This is going to be a raster file, and it's going to be using those 2 rasters from the list of rasters for Romanian population. So I'm going to open then these brackets, and then I'm going to take the second element of this country pop rasters, which is a raster for 2020, and then I'm going to say minus, and then I'm going to take the first element of country pop rasters, which is the raster for 1990. And that's basically it. This is how you calculate. So then what you will get is the difference in population between those two for every pixel. So for those pixels where there is, of course, no population, in both cases, it's going to be simply 0. Anyways, so this is the part that you can skip if you're working on a non-European country. This is where I want to reproject the whole thing into this Lambert projection. All right, now that we have the population change raster, we can go ahead and classify our categories. We're going to have 3 categories in total. The first category is going to be those values that equal 0. So basically they are not inhabited. The second category is going to be population growth. So those are the values that are higher than 0. And the third category is the population decline. So this is where the value is lower than 0 or it's negative. So let's go ahead and do that. And I'm going to show you a new trick how you can actually classify these different categories directly on the raster using Terra. So we're not going to be transforming into data frame and then performing. So I'm going to go ahead and create here a new function which is going to be called getCategories. So this function is going to accept an argument x. And then within this one, I'm going to use ifEl function from Terra. But I'm going to use multiple ifEl because here we have multiple conditions. So the first condition, as we said, is when population change equals 0. Then I want to return 0 here. The reason why I'm putting here 0 and not a string which says uninhabited is that Terra does not accept strings. It accepts numeric values or logical values. So we're going to go for numeric value. It's going to be like that. Now, because we have multiple conditions, we are continuing within this one, and we're using another ifEl here. So there's going to be another ifEl, and within this one, as we said, we want when population change is greater than 0, we want it to be, let's say, 1. So to denote these situations where population is growing. And then we have the final one, ifEl, which is for those situations where population change or pop change is lower than 0. Well, in this case, we can use, let's say, -1. And then here we need to close off this one with else statement. So if none of these things are there, you know, what should it be returned? So I guess that would be the case of missing values, which we don't have. But anyways, you need to return something. And let's say we're going to return this pop change. Okay, so once we do that, we need to apply this function to our pop change and to create a new one. So I'm going to go ahead and create an object called pop change cats, so categories. And then I'm going to apply this getCategories function to pop change. Okay, and then the very last thing is I want this to be a factor. So I'm going to be using as factor, just like this. So we have 3 categories in total. They start with -1, which is decline. Then they go into 0, which is for uninhabited places. And the final one is 1 for growth. The same way we organize these levels, we should also organize our colors. So here, the pink value that you can see denotes decline. The gray one denotes uninhabited areas. And finally, the green one I'm going to be using for growth. Once we have that, we can go ahead and use ggplot2. So I'm going to create an object called p. And of course, I'm going to start with ggplot here and then start adding things to it. Because we are here plotting the raster or the Terra using ggplot2, we need to use tidy Terra. And from tidy Terra, we need to use geom spat raster. So over here, we need to define our data. So our data in this case is pop change cats. All right. And that's basically it. So the next thing you can also do, you can add the national boundaries for your country. So in this case, we're going to be adding using that country as an object. Then, because we want the raster file to be visible, we will make this country boundaries shapefile transparent. And then in terms of the colors of the borders, we can go ahead and choose some kind of a gray. Let's say, for example, gray 40. So this one. And then finally, we can also choose the size of the border, let's say 0.5 inches. Okay, so that's about it. All the other steps are about basically customizing your options. And one of them is about adding, of course, the color to this plot. So for that, we use scale fill manual for a very simple reason, because we are dealing with categorical values. The first thing that I like to do is put here the title name. So I can, for example, frame it growth or decline, question mark. The second thing we can do here is define the values. We already have them. They are in this object called calls. And finally, we can add some labels, because I don't like really those numbers there. So you remember we start with -1, so that would be decline. I'm gonna call it decline here. Then remember the second one is 0, so that's uninhabited. And the final one is growth. Okay, now also I want to avoid situations where maybe my levels have some NA values, so around the plot. And for that I can use this option NA translate equals false. The next step is that you can define is the legend, how it's going to look like. For that we use guides. So because we're using a fill option in the main aesthetics, we need to use this one and then also define guide legend here. So what you can do is you can, for example, say how your legend is going to look like. I would like it to be horizontal. It could also be vertical, but let's say horizontal. That's the first one. Then you can specify some other things, like for example, key heights and also key width of your legend. So for these, you actually can use, let's say the width or the height can be, let's say 5 millimeters. And we can make the width a bit longer so it stands out. So let's say, for example, 40 millimeters. Okay. Then you can also, for example, specify label position. So I can maybe center the labels that we have. What else can I do? Well, label position actually needs to be a string. So I want it to be below the legend key, so it's bottom. But I can also horizontally justify, that's what I wanted to say. So for that, you can use label.hjust and mid-center it like this. We can also say that the number of rows is 1, but that's kind of obvious because the direction is horizontal. I would like them to be next to each other, those legend keys. So that's why I'm putting here by row equals true. And I would like to drop the categories that are not used. So for example, if there is something which is NA. Okay, so the next thing is the coordinate reference system. So this part, if you're not using that Alhambra projection, you can skip this, what I'm writing now, this chord SF equals 2. And then I'm using this because I did not reproject my national boundaries of Romania, so that country object. That's why I'm using here. I need to coerce it so that actually it aligns with the raster which is already in this Alhambra projection. So this line, 164, you can simply omit if you're not using this CRS Alhambra project or object. And then finally, we can go ahead and specify our theme. I like to start with theme void, which gets rid of some excess elements around the map itself. But I also like to use alongside this one theme itself, because it allows me to then specify some other things. And some other things that I would like to specify is, for example, legend position. I would like to position this legend to be in the middle. So I would like it to be mid-center or centered. And I would like it to be on the top. So I'm going to use the value which is 0.95. Then I can also specify legend title. So I can increase or decrease it. But for that, I need to define this as element text. So I need to tell ggplot2 that it's a text. So because I plan to increase a bit the size of the plots, I will go ahead and choose a bit bigger title, so 30 pixels. If it doesn't work for you, you can readjust it, no problem. And I'm gonna go ahead and use, for example, this charcoal gray for the color. I guess that's fine. I can also specify here a legend text. So I can simply copy and paste here this and change title to text. For the text, I can opt for something a bit smaller, but still kind of quite visible. Then one of the other things that we can do is, for example, we can do plot caption. Caption is also text here. I want to have a caption for the reason because I would like to put the data source there. So for that, we can go for, let's say, size 20 pixels, but it can be a bit lighter than this. I would like it to be also centered, and then I would like to push it a bit forwards towards the map, so that's why I'm using this v-just or vertical justification. Okay, now that we have this, we are almost done. One last thing is I would like to readjust a bit the margin, so that white space around the map in the following way. So I'm going to be using plot margin for that, very convenient function. You need to pass unit arguments to it, and then within this one you need to provide a list of 4 elements. So T stands for the top side. So for the top side, because my legend is there, I'm going to give it a bit more space. That's why I'm putting here 0.5. For the bottom part, I'm going to shrink it. So I'm putting here -3. For the left part, I'm also going to shrink it. And then for the right-hand side, I'm also going to shrink it using all the same values. If this doesn't work for you, you can also play a bit with these things, or you can just omit plot margin completely, this argument. So, apart from these things, what we also have here is labs, where we can define some things that we want to have. So I don't have a title, but I do have a caption, if you remember. So for caption, I would like here to put that the data that we're using here is global human settlement layer, and then we can do, for example, at 30 arc 6, for example. Okay, so this would be the code. It's quite long, but if you run this whole thing, the next thing is then to save this plot. And the way I would like to save this is, first of all, defining the dimensions. So I'm going to go ahead and say here that my width is going to be called W. It's going to be based on the number of columns of that raster file, which is called pop change cats. And the height here is going to be based on the number of rows. So this is how you get, this is a small trick, how to get a proportional figure or graph. And the next step, of course, is saving this using GHSL and then passing these elements to it. So for the GHSL, the first thing is, of course, the name of your file. So we can say Romania population change.png. This is also very important. Second thing is your object. So in our case, it's P. And then you can pass width and height. So for the width, we're going to go here for, so it's quite small because we want to go for pixels. And so I'm going to multiply by 5. So I'm going to get something like 5,000 by something pixels, which is, I think, totally, it's going to be a good one. And then for the height, worth remembering, you should use the same coefficient if you're multiplying here, dividing, or whatever you're doing, because you want to make sure that you have the same ratio. Finally here, I'm going to say that for units I'm using pixels. And then for the background, and this one is optional, I'm going to use white background. If you followed all the steps so far, you should be able to see the population change map of Romania that looks like this. And the results are quite shocking because there is a lot of decline across the map. In fact, it dominates the landscape. There are some islands of growth, but they're mostly reserved for urban places. One thing to keep in mind is that this map is based, of course, on the data that are estimates of population change. They do use the census data, but in the end, we should also take them with a grain of salt. And this is how you do it. In today's tutorial, you learned a valuable lesson: how to use global human settlement layer data to compute and then map population change. We use the example of Romania, but you can simply replace the ISO2 code with your preferred country ISO2 code, and then you can create some amazing population change maps for any country around the globe. If, however, you're interested in replicating today's analysis, I prepared a link to the GitHub repo in the description box below. Feel free to clone it, modify it, reuse it as you see fit. If you have any comments, questions, or just general feedback, feel free to reach out to me here on YouTube, but also on X and Instagram. If you are new to R and you seek to expand your data visualization and geospatial knowledge with R, I prepared a few cool tutorials for you, so do go and check them out. See you next time.